Hi, my name is Shavin Dehani and I'm presenting our work on robotic navigation autonomy for subretinal injection via intelligent real-time virtual IOCT volume slicing. Many medical treatments of eye diseases need precise subretinal drug delivery, which emphasizes on the importance of the autonomous systems in the eye surgery. The field of microscopy has made significant strides with the introduction of optical coherence tomography (OCT) and intraoperative OCT, which offers real-time 3D OCT imaging. Similarly, there has been significant progress in the development of robotic systems for eye surgery, which can achieve micron-level precision. In this regard, we propose a system and a workflow which tackles the task of autonomous subretinal targeting. We connect a processing unit with a Leica iOCT microscope and a robot, all communicating through ROS. Moreover, we design a workflow keeping the surgeon in the loop to choose a subretinal objective point for autonomous targeting. Our system is visualized in this picture. The steady-hand iRobot, Leica OCT integrated microscope, and the ex vivo porcine eye for the experiments. The main challenges which need to be tackled are as follows: injection needle pose estimation, retinal layer segmentation from iOCT frames, robot microscope registration, and trajectory planning. Approaching the segmentation problem as a 3D task would present certain challenges. The segmentation process of a volume and collection of a labeled dataset would be time-consuming. Moreover, due to the non-uniform spacing of the iOCT scans, the kernels used in convolutions would need to have non-standard sizes, making the training process problematic. To accomplish this, we take advantage of the shadowing effect present in the iOCT images. By averaging the planes of the volume along the z-axis, we can generate an axial projection image. This image serves as a map that identifies the parameters of a plane that fully contains the needle. We can extract this plane from the volume by interpolation and create a virtual B-scan that includes the needle. By adopting this approach, we can simplify the 3D segmentation problem into two 2D problems. To summarize, the approach for the needle pose estimation would be as follows: creation of axial projection image, segmentation of the needle shadow, fitting a line, estimation of the line parameters, extracting the virtual plane, segmentation of the plane, extracting the remaining parameters, and finally doing the needle pose estimation. We then receive a target point as an input, we do the trajectory planning, and then we execute. Once we have predicted the position of the needle with respect to the volume, we take advantage of the parallelism between the z direction of the volume and the z direction of the robot. This allows a straightforward conversion of any translation vector from the volume domain to the robot domain. We break down the translation between the initial position of the needle tip and the target point into two separate translations to ensure that the needle moves in the direction of its shaft when it comes to the contact with the tissue. This video showcases a complete demonstration of the system. Initially, a volume is obtained and the surgeon specifies an injection target point using the user interface. All the necessary computations are performed and the command is then transmitted to the robot. Finally, a second volume is obtained to demonstrate the end result. To evaluate our system, we conducted 10 experiments on ex vivo porcine eyes in open sky conditions and 10 experiments without any medium. In both cases, our system achieved acceptable performance, although we did observe higher errors in the animal experiments as expected. To conclude, we showed a system and a workflow which performs OCT-guided subretinal injections by introducing the concept of intelligent virtual B scans, which reduces a 3D segmentation problem to two 2D segmentation tasks. As potential next steps, we aim to develop a solution for faster acquisition of OCT volumes to enable closer to real-time processing. Additionally, we will recognize the need for non-rigid registration of volumes when acquiring real-time volumes. Furthermore, we need to incorporate not only translational transformations, but also RCM movements. Lastly, we plan to conduct further experiments on intact and in vivo porcine eyes. Thanks for your attention.